Hey everyone, and welcome. So, you've mastered differentiation, but that means you've only seen one side of the calculus coin. Today, we're going to flip it over and explore the other incredibly powerful half, integration. Let's jump right in. So think about it. You've gotten really good at finding the rate of change of a function, right? The gradient, the derivative. But what if you have the derivative and you want to find the original function it came from? How do you go backwards? Well, that is the big question we're answering today. Here's our roadmap. We'll kick things off with what integration actually is. Then we'll get into its two main flavors, the indefinite and the definite integral. And once we've got the tools down, we're going to put them to work on some really cool stuff, like finding the exact area of curvy shapes and even the volume of 3D objects. Sound good? Let's get to it. Okay, so let's start with the most basic question. What even is integration? Well, like we just said, it's all about going in reverse. It's truly the other side of the calculus coin. The easiest way to think about it is this. Just like subtraction is the opposite of addition, integration is the opposite of differentiation. They're inverse operations. So when we integrate, we're hunting for something called the antiderivative. That's the function that, if you differentiated it, would get you right back to where you started. It's basically a mathematical undo button. All right, our first tool in the toolkit is the indefinite integral. This is what we use when we want to find the general family of functions that could be our original answer. Okay, don't let all the symbols here intimidate you. Just look at that very first formula. This is the power rule for integration. Remember how with differentiation, you'd multiply by the power and then subtract 1 from it? Well, here we do the exact opposite. First, we increase the power by 1, and then we divide by that new power. See? It's a perfect reversal. Now, this next part is absolutely 100% crucial. You cannot forget the plus c. Seriously, it's the most common mistake people make. Think about it for a second. What's the derivative of x squared? It's 2x, right? But what's the derivative of x squared plus 5? It's also 2x. And x squared minus 100? Still 2x. That plus c is a placeholder for any constant that would have just vanished during differentiation. So you're not finding one function, you're finding a whole family of them. So if we have this whole family of functions, how do we ever find the specific one we're looking for? Well, we need a clue. We need what's called a boundary condition, which is really just a fancy way of saying a point, x, y, that we know is on the curve. The process is pretty simple. First, you integrate to get that general function with the plus c. Then you plug in the x and y values from your given point. And that's it. You just solve for c and you've pinned down the exact function from that entire family. Okay, so we've been finding functions. Let's switch gears to the next major player, the definite integral. And here, the game completely changes. We're not looking for a function anymore. Nope, we're looking for a single, specific number. Let's just focus on that first formula up top. This, right here, is the heart of the fundamental theorem of calculus. And the process is actually pretty straightforward. First, you find the antiderivative, just like before. We'll call it capital F of x. But this time, you evaluate it at the top limit, b, and then you evaluate it at the bottom limit, a. The very last step, you just subtract f of b minus f of a, and that simple calculation gives you the single numerical value you're looking for. This slide is super important because it clears up a really common point of confusion. Let's look at them side by side. On the left, the indefinite integral has no limits, and its answer is a function, f of x plus c. On the right, the definite integral does have limits, a and b. And its answer is a single number. Function versus number. That is the key difference right there. So what's the big deal about getting a single number? Well, this is where calculus gets mind-blowingly powerful. Let's check out our first huge application, calculating areas. So what is that number we just found with f of b minus f of a? Well, take a look at the little graph on the slide. That number is the exact area of the shaded region. It's the space trapped between that curve, the x-axis, and the vertical lines at A and B. And that's amazing. We can now find the precise area of almost any weird, curvy shape you can think of. Okay, finding the area under one curve is pretty cool. But what if you have two curves? How in the world would you find the area that's sandwiched right between them? The logic here is actually beautifully simple. If you look at the formula for the area between two curves, all we do is we create a new function. And that function is just the top curve minus the bottom curve. Then we integrate that difference between their intersection points. It's just like finding the area under the top curve and then subtracting away the area under the bottom one. leaving you with just the bit in the middle. Pretty clever, right? So if we can master 2D areas, can we push it even further? You bet we can. Let's level up and jump into the third dimension with volumes of revolution. The name here pretty much says it all. You take a curve, you rotate it a full 360 degrees around an axis, like the x-axis, and it sweeps out this cool three-dimensional solid shape. Yeah, this whole idea is about rotation. Just focus on that formula at the bottom of the page. Imagine taking one of those 2D areas we were just calculating and then spinning it really fast, 360 degrees around the x-axis. You'd create a 3D solid, right? Something that looks maybe like a vase or a bowl or a horn. And what's incredible is that integration lets us calculate the exact volume of that solid. And here's the magic formula to do it. It looks pretty similar to our area formula, but you'll notice two key differences. First, there's a pi out front, which makes sense, right? We're rotating things in circles. And second, notice that we're integrating y squared, not just y. That's because what we're really doing is adding up the volumes of an infinite number of tiny, paper-thin circular disks. Phew, we have covered a lot of ground. So let's take a quick moment to pack up and review what's now in your official integration toolkit. So let's bring it all home. We started with that one big idea. Integration is just the reverse of differentiation. From there, we saw that the indefinite integral gives us a whole family of functions with that all-important plus c. Then the definite integral came along and gave us a specific numerical value. But that number wasn't just a number. It was the key to unlocking these amazing real-world calculations, like finding the exact area under a curve or the volume of a 3D solid. So seriously, congratulations. By understanding both differentiation and integration, you have now unlocked the other half, the full power of calculus. And so I'll leave you with this final thought. We've talked about areas and volumes, but trust me, that is just scratching the surface. From physics and engineering to economics and even statistics, now that you have these tools in your hands, what real-world problems can you go out and solve?